Almost everyone gets this puzzle wrong, even brilliant. Mathematicians insisted the obvious answer was correct. 3 doors sit in front of you, hiding 1 car. And 2 disappointing goats. You pick a door, confident, certain your choice is exactly 50% right. Then something strange happens. The host opens a different door on purpose. He reveals a goat, then asks a simple question, do you want to switch? Your gut says it makes no difference, but your gut is about to be proven wrong. Here's exactly how the game works, so nothing feels confusing later. There are 3 closed doors labeled 1, 2, and 3. Behind 1 door waits a brand new car, behind the other 2, goats. You choose a door first, without knowing what's hiding behind it. The host, who always knows exactly where the car is, acts next. He never opens your door, and he never opens the door with the car. Instead, he opens one of the remaining 2 doors, always revealing a goat. Now only 2 doors remain closed. Your original choice and 1 other door. The host then offers you a choice, stay with your door, or switch. Most people assume switching or staying makes absolutely no difference at all. After all, 2 doors are left, so it feels like a 50-50 guess. That feeling is completely natural, and it is also completely wrong. The real answer depends on something almost everyone overlooks in the moment. It depends on what the host actually knew when he opened that door. Notice that the host never acts randomly here. Every single move he makes is deliberately constrained by what he already knows. That constraint is the hidden engine driving this entire puzzle, and most explanations skip right past it. Let's test your instinct before revealing anything. Just trust your gut for a second. If you had to bet right now, would you switch doors or stay put? Most people, including university professors, insist that switching cannot possibly help. When this puzzle was published in a magazine, thousands of readers wrote in furious. Even a mathematician with a doctorate called the correct answer completely absurd. So if brilliant people got this wrong, your instinct isn't broken, it's just human. Our brains crave simplicity, and 2 remaining doors feels perfectly symmetrical. But probability isn't about how many options remain. It's about information. And in this game, 1 player has far more information than the other. That player is the host, and his knowledge changes everything about the odds. Think about your original choice for a moment, made with 0 information. You had exactly 1 chance in 3 of picking the car correctly. That means there was a 2 in 3 chance the car was elsewhere. Nothing that happens afterward can erase that original 2/3 probability. The host's move doesn't randomly reveal information, it's carefully constrained. He knows where the car is, and he deliberately avoids revealing it. So when he opens a door, he isn't just giving you a hint. He's handing you concentrated information about the door you didn't choose. Your first pick still carries only a 1 in 3 chance of being right, but the unopened door you didn't pick now carries the other 2/3. It helps Toymagen tracking probability like tracking water. It doesn't vanish, it simply flows somewhere else entirely. Right now, all of that flowing probability has exactly 1 place left to go, the door you didn't choose. Here's the twist that breaks most people's intuition completely in half. The odds never became 50-50. They were never redistributed evenly at all. All of the probability that used to be spread across 2 doors just collapsed. It collapsed entirely onto the single remaining door you did not choose. That door is now twice as likely to hide the car as your original pick. This feels impossible because our brains don't naturally track hidden probability shifts. We see 2 closed doors and assume equal odds, but equal isn't guaranteed. Equal odds only exist when no extra information enters the situation. Here, the host is a walking, deliberate injection of extra information. And that single fact quietly rewires the entire probability of the game. Some people insist this is a trick of language, but the underlying mathematics is completely rigorous and repeatable. Every reputable statistics textbook confirms the same conclusion, using slightly different proofs and slightly different wording. Let's make this crystal clear using an extreme version of the exact same puzzle. Imagine instead of 3 doors, there are 100 doors in a long row. You pick 1 door, hoping desperately that you got impossibly lucky. The host then opens 98 other doors, revealing goats behind every single one. Only your original door and one other closed door remain in the entire row. Ask yourself honestly, do you believe you happen to pick correctly among 100? Or is it far more likely the car is hiding behind that other door? Almost everyone instantly sees it now. The other door is overwhelmingly likely. That's exactly the same logic hiding inside the original 3-door version. Switching in the 100-door version wins 99 times out of 100. In the 3-door version, switching wins exactly 2 times out of 3. Staying with your original choice only wins 1 time out of 3. Mathematicians ran thousands of computer simulations to confirm this exact result. Every simulation matched the math perfectly. Switching wins roughly 67% of the time. The uncomfortable truth is simple. Your first guess is usually wrong. Notice something interesting. The extreme version with 100 doors makes the hidden logic almost impossible to miss. Our intuition simply wasn't built to handle small numbers hiding large, lopsided probabilities like this. 1. So what's actually happening here beneath the surface of this puzzle? Probability isn't fixed the moment you make a choice. It can shift. It shifts whenever new information enters, especially from someone who already knows the answer. The host isn't neutral. His actions are shaped entirely by hidden knowledge. Ignoring that hidden knowledge is exactly why the classic 50-50 instinct fails. This same principle quietly shapes decisions far beyond a simple game show. Doctors weighing test results, investors reading markets, all deal with shifting information. Whenever someone with more knowledge acts, their action itself becomes a clue. The Monty Hall problem is a tiny puzzle hiding a massive lesson. Trust the math, not the feeling, because feelings ignore information that math cannot. This is why professional poker players, actuaries, and epidemiologists train themselves to distrust simple gut reactions. Updating your belief the moment new information arrives is a skill, and like any skill, it can be practiced. If this puzzle broke your brain a little, that means it worked perfectly. Comment below with your honest first guess before you learn the truth. Would you have switched, or would you have confidently stayed with your goat? Subscribe if impossible sounding logic puzzles like this one fascinate you, because next time, a mystery even stranger than this one is waiting for you.